Hello everyone, welcome back to our channel. Let's discuss the next topic, that is carbon magnetic resonance spectroscopy. Already we have a clear-cut discussion on proton NMR spectroscopy. In case of the proton NMR spectroscopy, we have observed that three isotopes for the proton, 1H1, 1H2 and 1H3. Among these three, highly abundant one is what? 1H1. 99.98 percentage we are observing 1H1. That's why the proton NMR peaks are highly incentive in nature. The intensity of the peak is very high. Now coming to the carbon. In case of the carbon also, we are having three types of isotopes: C12, C13 and C14. But the C12 isotope is highly abundant. But the thing is that it is magnetically inactive. Why it is magnetically inactive? Because of the presence of even number of protons and even number of neutrons. The spin quantum number is 0. That's why we do not have the concept of C12 NMR spectroscopy. This is very important question. Why are we having C13 NMR? Why not C12? The answer is the C12 is spin inactive. That's why it is magnetically inactive only. In case of NMR, spin active nucleus will be observed. So next one is C13 or not, but its abundance is very low, only 1.1. So its spin quantum number is 1 by 2. It is magnetically active. That's why we are having C13 NMR spectra. C13 natural abundance is very low, that is only 1.1 percentage, magnetically active, I equal to 1 by 2. C12 is highly naturally abundant, approximately 99.98 percentage, but the thing is that it is magnetically inactive because spin quantum number is 0. That's why we will not observe C12 isotope. Okay. So what is the meaning of that one? C13 is 1.1 percentage, means if you take 100 carbon atoms, among the 100 carbon atoms, 99 are C2. Only one is the C13. Because of that reason, the magnetic moment as well as gyromagnetic ratio of the C13 is very less than comparing with the proton. In case of proton, what happens? 1H1 abundance is very higher or not? 99.8 percentage. In case of C13, it is reverse. C12 is there, but no use because it is magnetically inactive. I value 0. So what the people are saying, the magnetic moment and the gyromagnetic ratio of the proton is 4 times higher than the C13. It is very important. Okay. So the disadvantages of C13 is what? Recording C13 NMR spectra is very difficult. Why? Because if you take 100 molecules, only one molecule. If you take 100 carbon atoms, only one carbon atom is magnetically active. Okay, lower abundance, lower magnetic moment and lower precision gyromagnetic ratio. Because of these reasons, it is highly difficult to record the proton NMR spectra. The C13 nucleus is less sensitive than the proton nucleus. Sensitivity means is to record signal, referred as the sensitivity. Okay, the recording of the signal is very much difficult. To overcome these disadvantages or the sensitivity problems of C13, PFT, pulsed Fourier transformation techniques are used by taking little larger quantity of sample in recording the C13 NMR spectra. Already we know that Fourier transform spectroscopic technique. Fourier FT-NMR, already we have a clear discussion in our videos. All the information is already available. Remember one thing, whatever the NMR technique is there, principle and instrumentation, both are common. It may be the proton NMR, it may be the C13 NMR, it may be the F19 NMR, whatever it may be. Principle is same, instrumentation is same. continuous waves NMR spectrometer we discussed, and also Fourier transform NMR. So both the things we already discussed, so you can see those videos as well. Okay, so in order to get the good spectra, what the people are suggesting, go for the Fourier and for transformation technique by taking the some amount of higher quantity of the sample. So by increasing the quantity of the sample, what happens? Number of C13 atoms will be increases, thereby we will get the good signal. Okay, see this one. Compared to the proton, C13 approximately 6000 times lesser sensitive. It means if you take 50 mg of proton, 50 mg of sample to record the proton NMR spectra, this is the intensity of the signal. The same amount you take and record the C13 NMR spectra, this is the intensity of the signal we will get here. Okay. Because of the lower abundance of C13, probability of finding C13 nuclei at adjacent positions in carbon skeleton almost ruled out. So with artificial enrichment possible to develop the carbon skeleton C13 isotope connectivity. So generally it is not possible to identify the adjacent carbons in a carbon chain because of the lowest abundance. That we need to remember, right? The next thing is, if you see the applications are similar to proton NMR. Nature of the carbon in a molecule we will be identifying by using C13 NMR. In case of the proton NMR, we are going to identify the behavior of the proton, nature of the proton we are identifying, right? In this way, the first application will be there. Second one, chemical equivalency, non-equivalency, how many number of protons attached to carbon skeleton, and environment of the each carbon group, stereochemical relationships, everything we can determine. The main application is this one. See this one. What is that? From CMR, possible to propose tentative carbon skeleton with protons connectivity. This is very, very important. Once we know the carbon chain in a molecule, automatically we can determine the structure of the unknown chemical compound. So this is the beauty of the NMR spectroscopy. That's why people will say whenever you are perfect in the NMR spectra, it means proton and C13 NMR spectra, you can be able to determine the structure with 99.9% accuracy. Okay, so this is the importance. Let's continue the equivalency and non-equivalency. In case of the proton NMR, we have two rules. One is the connectivity rule and second one is the substitution criteria. Here also same phenomena we are following. Connectivity rule means environment around the carbon. In case of proton, we have seen the environment around the proton. Now we have seen the environment around the carbon. Simple. Here see carbon connected to similar atoms. That's why only one signal. Here we have two carbons, but both the carbons are primary or not. That's why one signal. In case of the connectivity rule, simply follow the primary, secondary carbon atoms. Primary, secondary, tertiary, quaternary carbon atoms. If the carbons are different, different signals will appear. And also, we can identify the plane of symmetry. See this? If you identify the plane of symmetry here, we are observing plane of symmetry or not. So both the carbons are same. But in this case, the terminal carbons are same, but middle one is different. It is secondary or not? That's why two signals. If you see here, these two are same or not? That's why two signals. But in this case, these two are same and these two are same. That's why center one is different, so three signals. Whenever the electronegative group is attached to any carbon chain at the terminal, all carbons are automatically non-equivalent. So A and B, two signals. See how many signals are there? So in this way you can identify. Here see, plane of symmetry. Here no plane of symmetry. So all are different, three signals. Here plane of symmetry, that's why only two signals. Plane of symmetry, only two signals. No plane of symmetry, three signals. No plane of symmetry, three signals. Here plane of symmetry, 2 signal plus this one, 3 signal. Simply identify the plane of symmetry. Attachment, different attachment or different environment of the carbon. Very simple or not? In case of cyclic molecules, unsubstituted symmetrical cyclic molecules, all carbons environment same or not? That's why all will give only one signal. But in this case, see this one, plane of symmetry, these two carbons are same, but this one is different, two signals. Here also, these two carbons are same, center one is different. So two signals. Like that you can identify. In case of aromatic compounds also, identify the plane of symmetry. See, plane of symmetry. So these two proton carbons are same, these two carbons are same, this carbon is different, this carbon is different. So total how many signals? 4 signals. Unsubstituted, all carbons are same. Here in this case, 1, 2, 3, 4, and the functional group containing carbon is also different. Okay, environment is different. Simply, carbon environment is different, that is chemically non-equivalent. That many number of signals will be appeared. In case of biphenyl, see this one, two plane of symmetry. This is one plane of symmetry. This is one plane of. Always try to identify the plane of symmetry. Simple way, blind way. Okay. In case of disubstituted, take the plane of symmetry here. These two same, these two same, these two same. Three signals. Okay. Here, take the plane like this. X, X, na. These two same, these two same, these two are different. Four signals. Here, same substitution. Take two. This is one plane of symmetry. This is one plane. These kind of molecules are very much important. In the examination, people will ask you non-equivalent sets of protons. Identify the non-equivalent sets of protons. That is very, very important. You need to identify. Okay. Next, if you have different substitution, no plane of symmetry, so all carbons are non-equivalent 6. All carbons are non-equivalent 6. But here see, one plane of symmetry we are observing, even though X and Y are different. These two are same and these two are different. Okay. Like that, we need to identify different kinds of the environment around the different kinds of protons. Thereby, we will observe the non-equivalent sets of carbons. Okay, see this? BR same. Take the plane of symmetry. So these two are same, these two are same, these two are same. So 3. If you take BRCl, all are different or not? No plane of symmetry, so 6. In this way also similarly, these two are same, but this one is different. So all are different. These two are same, this one is different. But here see this, here there is a chance for the plane of symmetry. AA, BB, but C and D is different. Like that, we need to identify different non-equivalent sets of protons. These are all the examples. You can go through it carefully. Naphthalene, durine, anthracene, phenanthracene, all kinds of things. Identify all these. Blindly follow plane of symmetry criteria. These are all very, very important examples. In the examination, you will find out all these examples. So try to have all these. Next. Already we know that connectivity rule and substitution method. In substitution method, what we need to do? We need to replace one of the atom with the third atom. Because of the replacement, if the obtained product is similar, then equivalency. If the obtained product is different, non-equivalency. See this. Here we have two carbons or not? First carbon and second carbon. Suppose at the first carbon, one hydrogen is replaced with Cl. What you will get? CH3, CH2, Cl. The second carbon, one hydrogen is replaced with Cl. So these two products are same or not? That's why C1, C2 both are same. Okay. Here see. Here if you substitute, both are same. That's why same. But here if you substitute third group, you will come up with what? 2-chloropropane. Okay. In case of aromatic compounds, the ortho, meta, para, H1, H2, H3, if you consider, if you want to say whether these three are equivalent or non-equivalent, what should you do? Replace with third atom. First one is giving the orthobromophenol, second one giving metabromophenols, third one giving parabromophenols. So three products are different or not? That's why H1, H2, H3 are different. Okay, in this way we can identify. In case of the naphthalene, anthracene, whatever it may be. Like stereochemical relationships also we can do in the same way. Diastereomeric carbon chemically non-equivalent. See this diastereomeric nature, cis trans isomerism. With respect to this particular group, this is see trans in nature, this one is cis in nature. Same. That's why this CH3, this CH3, both are chemically non-equivalent. Here, in that way you need to equatorial and axial carbons are chemically non-equivalent. Exo-endo are non-equivalent. Okay, syn anti are non-equivalent. Like that we need to identify different sets of protons. Okay, this is all about the chemical equivalency and non-equivalency sets of protons. Next come to the chemical shift values. Very important topic, chemical shift. See, principle is same for all chemical shifts and proton NMR, C13 NMR, F19 NMR, Ble11 NMR. The concepts are same. Okay. Now come to the values. The values will be changed. In case of the proton NMR, the chemical shift value range is 0 to 20, right? But in case of the carbon C13 chemical shifts, which are very much higher, see, carbon nucleus is more sensitive for the change in the chemical environment compared to the proton nucleus. Therefore, delta chemical shift values are larger as compared to the proton. The people will ask you in the interviews why the C13 NMR chemical shift values are higher than the proton NMR. The reason is this one. In case of the proton, what happens? We have only s orbital or not. Because of the s orbital, what is the environment? Spherical environment or not. That's why symmetrical distribution of the electron density around the nucleus. Thereby, whenever the external nuclear external magnetic field approaches to the proton nucleus, the effect is same around the nucleus. But in case of the carbon, what happens? Along with the s orbital, we are having the p orbital also. S orbital means this is the circle one, p orbital means this is the dumbbell, right? Because of the presence of the p orbital, here the distribution is unsymmetrical distribution. Because of the availability of the unsymmetrical distribution, what happens? The external field may approach in this way, or the external field may approach in this way. It means that what? At one point of time, the complete external field can completely influence the nucleus or not. 100% influence of external magnetic field on the nucleus. Already we know that the precessional frequencies are directly proportional to the strength of the external magnetic field. If this nucleus experiences 100% influence of the external magnetic field, automatically what happens? 100% precessional frequencies will be increased or not? If the 100% precessional frequency increased means what happens? 100% chemical shift value will be increased or not? That's why, because of the availability of the non-symmetrical nature, at one point of time the nucleus experiences 100% the strength of the external magnetic field. That's why the probability for the higher values of chemical shifts. Okay, this is the thing. So here also tetramethylsilane is reference standard, always taken as 0. The range is this 0 to 250. In case of proton, that is only 0 to 20. Factors influences There and here similar hybridization, nature of hybridization, electronegativity, anisotropy, conjugation, whatever the factors which we have discussed, there similar kind of factors are discussing here also. See, there also according to electronegativity, sp hybridized proton should be having higher delta chemical shift value, but very lesser or not. Already I explained the reason. The same reason applicable here also. I am not again explaining. Check the previous video. Okay. Conjugation can also affect. Suppose whenever these kind of double bond is attached to electron withdrawing group, what is happening? See this, these pi bonding electrons moving like this or not? That's why beta carbon is getting the positive charge or not? Positive charge means electron deficiency or not? That's why beta chemical shift values are higher. In case of electron releasing, what happens? The beta carbon getting the minus charge. Electron density more means applied field less, frictional frequency is less, chemical shift value is less. Okay. Next is steric crowding. If the steric crowding is there, chemical shift values will be less. In the absence of the steric crowding, chemical shift values are higher. Same factors, whatever the factors we discussed in case of proton NMR, here also same. Here one more thing is that by increasing the heavy atoms at the carbon, by increasing the number of heavy atoms at the carbon, chemical shift values will be decreases. See here, top to bottom, chemical shift values are decreasing. Why the chemical shift values are decreasing? According to electronegativity, top to bottom, delta chemical shift value should be increases, but due to the steric crowding, top to bottom delta chemical shift values decreases. Crowding is dominating here. So electronegativity is suppressed, neglected, steric crowding is considered. So the thing is that according to electronegativity, top to bottom the value should be decreases, but due to the higher electronegativity and steric crowding effects, according to electronegativity factor, the delta chemical shift values from top to bottom should increase, but there is a decrease in the delta chemical shift values due to the heavy atom effect. Okay, then decrease in chemical shift values due to the heavy atom. Gamma Gaussian effects, this is very important one. What the people are observing at the terminal, if you have more electronegative atom, what happens? The influence will be there. That's why immediately attached carbon chemical shift value will be more comparing with the remaining carbons in the carbon chain. See this? So according to this scenario, what happens from this way, what we need to observe, the delta chemical shift values should be completely decreased. But if you see 50, 40 decreasing, 25 decreased, again 29 it is increased. With respect to this one, this is alpha carbon, this is beta carbon, this one is gamma carbon. At gamma carbon, what is happening? The chemical shift value is drastically decreasing. Again, delta increases. The effect is commonly called as gamma Gaussian effect. Why the unexpected decreasing in the chemical shift value at the gamma position? The reason is steric crowding. In the Gaussian conformation, see this one. This is the electronegative group which we have attached at the carbon chain terminal. Thereby, with respect to OH, the alpha, beta, gamma. So, with respect to OH, this is gamma position. In the Gaussian form, what happens? OH and this group is experiencing more crowding. Because of the more crowding, what happens? The chemical shift values are slightly decreasing. This is gamma Gaussian effect. Okay, you need to remember. So these are the chemical shift values everyone needs to remember. If you know very well the chemical shift values, you can easily identify the unknown structure of the chemical compound. Okay. This is the range. Different functional groups are coming under these categories. Coupling constant. Already we know that distance between the adjacent lines in a NMR signal is commonly called as coupling constant. So here we are ruling out the homocouplings are not C13, C13. Why? Because of lesser abundance of the C13. So here we are having two types of coupling, short range and long range. That short and long range is due to the C13 proton, heteronuclear coupling only. This is one bond separation only, short range coupling. If you see this one, C13 and this hydrogen, or C13, this hydrogen, this is called as long range coupling. In this case, direct attachment, there is no direct attachment. In between these two, one carbon is there. In between these two, two carbons are there. These are called long range couplings. Long range couplings are allowed. So in case of long range couplings, this is the J value. Okay, long range. In case of short range coupling, this is the J value, 125 to 250 Hz or ppm. Long range means what happens? Strength will be decreased or not. That's why automatically J value will be decreased. The chemical shift values and J values are like this: 0 to 250 Hz and 0 to 250 ppm in case of C13 NMR spectra. Okay. Similar, J values are depends on the nature of the hybridization, electronegative atom, ring strain, dry hydrogen angle. Already we know that percentage of character increases means J value increases. In case of SP, percentage of character is higher. That's why J value is more than comparing with this one. With increasing the electronegativity of the atom, the delta chemical shift values and the coupling constants increases. See this one from top to bottom. What is happening? The strength of the J value is increasing. With increasing the ring strain, the J value increases. So from bottom to top, J values increases. This is all observed. In case of the aromatic compound, if you have a substituent here, if you have any substituent here, with respect to this ipso position, we have that ortho meta para protons. The meta protons J value is slightly higher. In case of vicinal, this is the equation which we have. Okay. Now the last and important topic is types of C13 NMR spectra. Broadband decoupled spectra, off resonance decoupled spectra, and selective decoupled spectra. Already we know that in case of the proton NMR, we have observed spin-spin coupling. What is the spin-spin coupling? If you have this kind of moiety, if you have two different non-equivalent sets of protons, always coupling takes place between them. That's why HA will give the doublet to HB, HB will give the doublet to HA. Because of the spin-spin coupling, what happens? The complexity of the spectra increases or not. In order to reduce the complexity, what we need to do? We need to include the concept of decoupling. Decoupling means elimination of the coupling interaction between the adjacent protons, commonly called as decoupling. How we can do? We need to supply two different, see, HA have some frictional frequency, HB have some frictional frequency. So we need to supply certain frequency, thereby flipping of the nucleus takes place, thereby the adjacent proton cannot identify this proton. That concept is commonly called as decoupling, clearly explained in case of the proton NMR. So all are requested to check those videos related to the decoupling spectra. Right? See this one. Elimination of coupling interactions between the neighboring nuclei, commonly called as decoupling. One of the factor for the complexity of the spectrum is splitting of the signal. That's why we need to do the decoupling. In order to prevent the splitting of the signal, decoupling techniques are used, which makes the spectrum simple. These are also called as double irradiation or double resonance. Already we have a clear-cut discussion on the double irradiation or double resonance phenomena. Now come to the first type of decoupled C13 NMR spectra, that is Broadband decoupled spectra. This is also called as noise decoupled spectra, proton decoupled spectra, completely decoupling spectra, and coherent decoupling spectra. These are the other names of broadband decoupled spectra. The name itself indicates broadband. This simply states that in any organic molecule, if we have C13 interactions, C13 proton interactions, eliminate all kind of coupling interactions, then the spectra is called as broadband decoupled spectra. We may have different kinds of carbons or not. Eliminate all kind of interactions. The interactions may be C13 interactions. The interactions may be C13 hydrogen short range coupling. The interaction may be C13 hydrogen long range couplings. Eliminate all. Thereby what happens? The spectra will be clean. For every kind of carbon, you will get a singlet. So in case of broadband decoupled spectra, we will observe all the signals as singlets only. All the signals as singlets. See this. All types of C13H couplings interactions will be eliminated. All short range as well as long range. For that purpose, what should we do? By irradiating sample with radio frequency radiation having the range of frequencies, broadband range. We have, suppose for example, we have 5 types of couplings. In order to remove the 5 types of couplings, we need to give the 5 types of radiations. Radiation is one, but different frequencies. Okay. So every non-equivalent set of carbon is appear as a singlet. That's why splitting of the signals stopped, signal intensity increases. Number of signals in the spectrum equal to the number of non-equivalent sets of carbons. The disadvantage of DBZ is that what? We are going to completely remove the CH interaction, CH connection, loss of CH connectivity. Okay. In case of the proton NMR, signal intensity is directly proportional to the number of contributing protons, but that is not possible. In C13 NMR, signal intensity not only proportional to the number of nuclei contributing it, intensity of the signal also depending upon the NOE, nuclear over-Hazer effect. The coupling takes place through the space, already discussed, and protons attached to the carbon, both the things. Here only carbons, here NOE and protons. With increasing the number of protons at the carbon, the intensity of the signal will be increases. Suppose see this one, CHO, CH3. This is one type of carbon, this is another type of carbon. In between those two carbons, we may have coupling or not, but that is ruled out. In between carbon and hydrogen, we may have coupling, that is ruled out. In between carbon and hydrogen, there might be a coupling, that is ruled out. That's why we are getting two signals, two singlets only. But this intensity is less and this intensity is more. Why? Because more number of protons present at this carbon. That's why intensity is higher. Okay. See this. Intensity order. The number of protons increases, the intensity will be increases. See CH4 one signal, CH3 CH3 one signal, CH3 two different kind of protons, then only singlets will be appeared. 2 protons lesser intensity, 3 protons higher intensity. Okay, these two are same. Two types of signals are there. Only all are singlets only. The next type is off resonance decoupling C13. This is very important NMR technique. Everyone should remember this technique only. Based on this technique, we will identify number of signals in a C13 NMR spectra, right? Here what we are doing, we know that two types of couplings are there, C13H short range coupling and C13H long range coupling. Here what the people are doing, they are allowing C13H short range couplings. If the hydrogen is directly connected to the proton, now connected to C13, These couplings are only allowed. This is the example of short range or not. So all short range couplings are allowed, all long range couplings are removed by using the decoupling, by using double irradiation. The technique is commonly called as off resonance decoupling. See, except one bond separation, C13 coupling, residual coupling, all other couplings, long range couplings will be eliminated by irradiating with the corresponding frequency. Signals appears with the multiplicity due to the C13 hydrogen interactions. Here the multiplicity gives the number of signals or not. For that we need to follow n plus 1 rule. N indicates number of hydrogens at the carbon series. There is no carbon, there is no hydrogen at the carbon, that will be appeared as a singlet. If one hydrogen is there, doublet. If two hydrogens are there, triplet. Three hydrogens, quartet. Like that we need to observe. But in case of analysis, how can we observe? In C13 NMR spectra, if you observe a quartet, that directly state that the carbon containing three hydrogens. For a C13 spectra, for a carbon, if you observe a singlet, it means only carbon is there. There is no attachment of proton. If a singlet is appeared, like that, if a doublet is appeared, that indicates that at least one hydrogen is present at the carbon. Like that we need to identify. Very simple or not? See this one. Here we have two types of carbons or not? This is A type, this is B type. So two signals we will get or not? For this C double bond O, there is no attachment now. Which attachment? Hydrogen attachment. That's why it appeared as singlet. For the carbon, how many protons are attached? 3 or not? N plus 1 rule. 3 plus 1 means 4 signals means quartet or not? 4 signals. Very simple or not? In case of proton NMR, the signals are writing in this way, right? But here we will write the straight lines. In case of C13, that you need to remember. Next, selective decoupling. The name itself indicates selective decoupling. See this one. Here is an example. For A-type protons, carbon, for A-type carbon, 2 protons attached. 2 plus 1 means 3 signals or not? 2 plus 1, 3 signals. For C carbon, 3 protons are not. 3 plus 1 means 4 signals are not. See the B. At the B, how many protons attached to carbon? Only 2 protons are not. So according to criteria, 2 plus 1 means the signal should be 3 or not. But what is the signal? Only singlet. That means what we are doing? Here we are doing the decoupling. Here we are applying the decoupling. For a selected carbon, if you apply decoupling, then the technique is called as a selective decoupling technique. The selected carbon will appear as a singlet in the spectrum. Okay? The selected carbon will appear as singlet in the spectra. See this one? This is the example. For this example, we will identify all types of decoupling. In case of broadband decoupling, what happens? All types of carbon will be appeared as a singlet. See, all are appearing as a singlet. But the intensity is more for the higher hydrogens containing carbon. See this? 3 higher hydrogens, 2. In case of off resonance decoupling, what we need to observe? If one carbon containing one hydrogen, 1 plus 1, n plus 1 rule we need to apply. See, CH3 means 3 plus 1, 4. CH3 means 3 plus 1, 4. CH2 means 2 plus 1, 3. CH2 means 2 plus 1, 3. C double bond O means no attachment of hydrogen, so singlet. Okay, intensity is based on the number of hydrogens. Number of hydrogens increases, the intensity will be increases. So in case of selective decoupling, suppose I don't want the coupled spectra of this carbon, then the CH2 will be appeared as a singlet or not? this CH2 will be appeared as a single. So in this way, we need to identify the spectra of different organic compounds by using the C13 NMR. So I request all the aspirants that before entering into the concept of the C13 NMR spectroscopy, try to complete proton NMR spectroscopy with 100% accuracy. Then only C13 NMR will be very much easy to all of you. Okay, thank you very much. All the best.